Swayam Prabha. Digital India. Educated India.
Hello everyone, I hope you are enjoying all the lectures happened so far. This is your lecture 5 of module 2. So in this lecture we are going to cover some more details about Snell's law, and then we will be talking about takeoff angle and the transmission and the reflection coefficients in the case of PSV and the SH waves that are incidenting upon an interface. And then we will be also describing about the Fermat's principle, and then later on we will be having some glimpses of Huygen's principle. So in the previous class we covered some details about Snell's law, where we saw that the horizontal apparent velocity across the interface should be equal, that is separating two media, medium 1 and 2. So in the previous class we saw that, let's suppose this is an interface and there is a wave that is incidenting upon this interface and it is making an angle, suppose I, then it is transmitting into the medium, that is medium 2, and having its refraction angle as R. Then we can equate the horizontal apparent velocity, that is Cx, across this interface. So Cx for medium 1, if suppose this is your medium 1 and this is the medium 2, and in the medium 1, let's suppose the velocity of the wave is v1 and this is the v2, then the Snell's law that we can write, if we impose the continuity of Cx, that means the apparent horizontal velocity across this interface should be equal. That means Cx in medium 1 and medium 2 should be equal. And when we do so, then what we get is sin I by V1 will be equal to sin R by V2. And this basically nothing but it is a ray parameter of the wave. And we also discussed that the ray parameter along the entire path of the ray is equal, and at each point of the ray parameter will remain constant. So that is what we are going to see in more detail in case of we have a stack of layers. That means instead of having only the single interface, if suppose we are approximating the earth as an onion shell where the properties may change as you go down but do not change laterally, which means if we are considering that the earth is made up of a several stack of layers, something like this, then how can we write the Snell's law? How the Snell's law will be valid in case of the stack of layers, or the stack of layers that we are considering are isotropic in nature and each layer is homogeneous in nature. So in that case the Snell's law can be written sin theta 1 by V1 is equal to sin theta 2 by V2, or maybe equal to sin theta by 3 by V3, that will be equal to the ray parameter. Or in general we can write sin theta I by V1 Vi. So this is the geometry that basically represents the values of theta 1 and theta 2. So there is this wave that is incidenting upon this interface, having the incident angle theta 1 and having the refraction angle in the second media having velocity v2. The refraction angle is theta 2. And then when it emerges out into the medium 3, then the angle of refraction is theta 3. And the velocities of V3 is greater than V2, which means this V1 is less than V2 and V2 is less than V3. So as per our Snell's law, in the generalized form, what we can write is sin theta I plus 1 by Vi plus 1 is equal to theta I by Vi. Or if we want to find out the angle at which the ray will be refracted into a medium that will relate to the velocity of that medium and the velocity of the medium above and the incident angle of the wave in the medium above, then it can be written something like that: theta I plus 1 is equal to sine inverse velocity of the medium into which the ray is refracting, and divided by the velocity of the medium in which the ray is incidenting, and that will be multiplied with the sine of the angle for the ray that is incidenting in the medium above. So that is the generalized form of the Snell's law. So there can be two cases in which what we can consider this sine inverse, this value, if suppose it is equal to 1 or if suppose it is greater than 1. So these cases may be something like that, when the value inside the arc sine is equal to 1. When it is equal to 1, that means you are solving for sine inverse 1. That means theta I plus 1 will be 90 degree. So what can be this case? That means if suppose there is this interface and there is this normal onto the interface, and ray is incidenting onto this interface something like this, and when the angle of theta 1 is somewhat theta I plus 1 will become 90 degree. That means ray is going to travel, the refracted ray is going to travel along the interface. So that will make the angle 90 degree here. So that means it will happen at the value of the critical angle, where the ray will be having its path along the interface. The incident angle will be equal to the critical angle in that case. And when you have the sine theta 1 vi plus 1 by vi greater than 1, which means that the theta I plus 1 is going to be undefined, because sine do not have the values greater than 1. So in that case, the angle of refraction theta I plus 1 in the I plus 1th layer will be undefined, and all the energy will be reflected back, and there will not be any transmission in the second layer. So now let's talk about the takeoff angle a bit. So what is takeoff angle? So takeoff angle, as per the definition, it is the angle at which the ray leaves from the source measured in the plane containing source and receiver. So let's suppose, as per this geometry, here this source is located over here, and this is the source, and this is the ray which is basically emanating from this source. If you talk about the earthquake, let's suppose this is the location where the earthquake is happening or earthquake has happened. Then the energy will be leaving in the form of the wave fronts. So we are going to talk about a particular ray that will be perpendicular onto the wave front. Let's suppose this is the wave front, and we are talking about this ray only, and this ray is emanating from this source at an angle theta naught from the vertical. So this theta naught is the takeoff angle, because this is the angle at which this particular ray leaves from the source, and when it emanates and it will hit this interface and getting refracted at an angle theta 1. So what basically will happen, that if suppose this is an earthquake source and under which you have several layers, because we are considering the earth as an onion shell where the layer properties in a particular layer does not vary literally, and the properties of the layers as you go deeper down the earth are going to have variations. That means if we talk about the velocities are going to keep on increasing if we are going to talk about the normal earth. So in that case, because the velocity of this particular layer, let's suppose it is v1 or it is v2, then v2 is greater than v1. So when that will happen, what will happen, as the ray will leave from the source which reach to the interface, then it will bend away from the normal. So likewise it will keep on bending away from normal, and the one point will come when it will turn up. So when it will turn up, then it will start to refract back onto the surface. So it will takeoff angle does talk about the distances traveled by the ray. If the takeoff angle is higher, that means the ray will travel the shorter distance along the surface. If the takeoff angle is smaller, that means the ray can travel the larger distances on the surface. So this is the how it works. You can say this is one of the geometry that we have drawn or we have taken from Stein and Weissation book. You can see that there is this earthquake that is happening, and there are the rays. There is one ray that is leaving from this source. There is another ray that is leaving from the source and reaching to the seismic stations located on the surface. So if we talk about this ray, then this ray is having the takeoff angle I2. Another ray is having takeoff angle I1. So you can see that I2 is basically greater than I1. But when you look at the distances traveled by the ray having the takeoff angle I2, it is basically having the shorter distance onto the surface than the one which is having the takeoff angle I1. So what you can conclude is that how far the ray travels depends upon its takeoff angle. Rays with larger takeoff angles leave the source closer to the horizontal and travel shorter distances than with smaller takeoff angles. Now, let us talk about the reflection and the transmission of SH, P and SV waves. So before we are going into talk about the P and SV waves, we are going to first talk about the SH wave. So let's suppose there is this downgoing SH wave here. This is the downgoing SH wave. And when it hit the interface, this is the interface here. When it hit it, then what will happen? Then, as I told you in my previous lectures, when SH wave hit any interface, then only a reflected SH wave will occur and a transmitted SH wave will occur. It will not give rise to the P and SV waves. So P and SV waves are coupled with each other. SH wave is independent. So SH wave, when it is incidenting upon this interface, then it will give rise to the reflected SH wave, and there will be a transmitted wave which will be SH as well. So when it is hitting the interface at incident angle J1, the reflected angle will also be J1, and the transmission angle or the angle of refraction will be J2. And the velocity in the medium 1 is beta 1, that is the shear wave velocity or SH wave velocity you can say. And in the medium 2, the velocity is beta 2. And this entire geometry that you are seeing, this entire geometry is in XZ plane. So the vibration of the SH waves, or you can say the displacement of the SH wave, will be in the Y direction. That means perpendicular to the screen. So now let us consider a downgoing SH wave which has displacement in Y direction. So you can say the UX will be 0. The displacement in X direction due to SH wave will be 0. Likewise, the displacement in Z direction will also be 0, but there will be non-zero component along the Y direction, that is UY, and it will be depending upon the X, Z, T. That means UY as a function of X, Z, T. So now, in order to solve for reflection and the transmission coefficient for the SH wave, so basically what we want to do, we want to find out how much amplitude of the SH wave is going to be reflected and how much energy of the SH wave is going to be transmitted. So in that case, we are going to apply two boundary conditions. So what are those conditions? So let's suppose this interface is located at Z is equal to 0. So the boundary conditions that we can apply is the wave is continuous. The wave is continuous, which means the displacement across this interface are equal. That means Uy minus will be equal to Uy plus at Z is equal to 0. So that is what we are going to apply in the first boundary condition. This is your second boundary condition that we are going to have. That is the tractions are equal. That means T minus at Z is equal to 0 will be equal to T plus at Z is equal to 0. Okay, the tractions should be equal. Now let's have a recap of what we have seen as in formulas for the wave number, ray parameter and the horizontal slowness, vertical slowness, etc. So if you remember, we had talked about the slowness vector. So slowness vector can be decomposed into two components. So let's suppose this is your slowness vector, and it can be decomposed into your horizontal component and into its vertical component. If suppose this is your u vector, then this is ux, and this may be your uz. So now the slowness vector can be decomposed. The horizontal slowness vector is also can be represented by p, and the vertical slowness vector can be represented by neta. Now the p is basically equal to the sine theta by v, and that can also be equated to the horizontal wave number divided by angular frequency, and likewise you have this vertical slowness that is cos theta by v, and that is basically your kz by omega, vertical wave number divided by angular frequency. Now the harmonic wave propagating in xz plane can be described as, now you can write the harmonic wave equation for the harmonic wave in xz plane as this, where u is equal to ae to the power iota omega t minus k vector dot x vector. Similarly, ae to the power iota omega t minus kxx minus kzz. So what we have done, this wave number has been decomposed into its horizontal wave number and the vertical wave number. Since wave is downgoing, so what we are doing, we are taking this z as negative, because wave is going, because z is positive downward, so that's why this negative term is there, and that can be written as, if we take omega outside, that means a to the power iota omega, then in bracket what you will be left with t minus px minus neta z. And this particular thing we can write it in terms of overall slowness, ae to the power iota omega in bracket t minus s vector dot x vector. So this is the equation of the harmonic wave, and now you can write the equation for sh wave vibrating in only y direction. So what is that? You can write uy is equal to ae to the power iota omega t minus kxx minus kzz. So this is the equation of vibrating sh wave in y direction, because sh wave is having its vibrations in y direction, so displacement will occur in y direction, and that will be having this equation. Now let's define one more parameter here, that is the ratio of vertical to horizontal wave number. So the ratio of vertical to horizontal wave number can be represented by this particular parameter r alpha comma beta. If we are suppose talking about only p wave, then it will be r alpha. If we are talking about only s wave, then it will be r beta. So basically it is nothing but it is the ratio of vertical to horizontal wave number. So in case so that is kz alpha comma beta divided by kx. So if suppose we are talking r alpha, then it will be kz alpha by kx. If we are talking r beta, then it will be kz beta by kx. So you can see that the vertical wave number is basically changing. There it is associated with p wave velocity in case of r alpha. It is associated with shear wave velocity in case of r beta. So vertical wave number kz alpha comma beta will change with the velocity of the medium, while kx will remain unchanged even though the medium changes. So now look at that geometry we have just seen. So in this geometry the similar things are there. So the medium 1 is having the parameter mu1, rho1 and beta 1. Mu is the shear modulus, rho is the density of the medium, and beta 1 is the velocity of the shear wave in medium 1. And in medium 2 the shear modulus is mu2, and the density of medium 2 is rho2, and the velocity of shear wave in medium 2 is beta 2. And the SH wave incidenting upon this interface at an angle J1, and the incident wave is having its amplitude B1, and reflected wave is having its amplitude B2, and the transmitted wave is having its amplitude B dash. So in top medium, the total displacement in top medium, we can write something like this. So B1 e to the power iota omega t minus kx minus kzz. So this minus term is there because this ray, this is for incidenting ray, so it is going downward. So that is why it is written like this. And for the ray, that is the reflected ray, for this we can write B2 plus B2 e to the power iota omega t minus kxx plus kzz. So this plus sign is there pointing towards the ray is going up. So finally what we can write, if we want to replace kz with r beta 1 and kx, then what we can write, if you want to write, let's suppose let's define r beta 1. Beta 1 is the velocity in medium 1. So r beta 1 is equal to kz divided by kx. So the kz can be equated to kx r beta 1. So now we will replace it. Then what you will get b1 e to the power iota omega t minus kxx minus kx r beta 1 z plus b2 e to the power iota omega t minus kx plus kx r beta 1 z. Now the displacement in the bottom medium. So why we are trying to find out the displacement? Because the first boundary condition is the displacement is continuous. So what we are going to do in the bottom medium, uy plus in bracket x comma z comma t will be equal to b dash, that is the amplitude of the transmitted wave. Because the wave is going down, so there will be a plus term. So e to the power iota omega t minus kxx minus kx r beta 2. R beta 2 is what? R beta 2 is equal to kz by kx. Okay, so this kz will be depending upon the beta 2. Okay, now if we want to write the kz beta 2, that is equal to how much? That is equal to kx into r beta 2. So that will be replaced here. That is replaced here, kx r beta 2 z. So as per the boundary condition, the displacement across the interface are equal. So across the interface means here this interface z is equal to 0. So when you are incorporating z is equal to 0 in uy minus and uy plus, then what you will get? You will get something like this over here, right? So when you will do so, these common terms will be cancelled out, and what you will be left with, b1 plus b2 is equal to b dash. So this is your first equation. Now the second equation will come from the boundary condition of the tractions, and tractions across the interface z is equal to 0 must be equal. That is ti minus at z is equal to 0 is equal to ti plus at z is equal to 0. At the boundary, what you can see, like this is the interface, that is z is equal to 0, and this is your x direction and this is your z direction. So the normal vector onto this interface at this boundary, you can see that n cap is equal to 0, 0, 1. And from the Cauchy's stress theorem, the traction vector can be written sigma ij and j. So this is your normal vector, and and the normal vector along the other direction nx and ny will be equal to 0. So what you will get, this will reduce the tractions equivalent to something like this. Tx is equal to sigma xz nz, or you can say sigma xz. This should not be there. And ty is equal to sigma yz, nz is equal to sigma yz, and tz is equal to sigma zz, nz is equal to sigma zz. So basically the SH wave is vibrating in the y direction. The only non-zero stresses will be sigma yz. But let us show this and now solve for the traction at the interface. So let's see how this traction will be having the non-zero stress only along the y direction, and that is sigma yz. So let's see how it is. So for an isotropic medium, we can write the Hooke's law in the form of Lami's parameter lambda and mu, something like this in the Einstein notation. And in the Einstein notation, it will be sigma ij will be equal to lambda E kk delta ij. Delta ij is the Kronecker delta function, plus 2 mu E ij. When you will expand it and write it in the matrix form, the stress tensor may look something like this. And you know that the value of ux and uz are basically equal to 0, because the vibrations are happening only in the y direction. So only non-zero displacement will be uy. This will not be equal to 0. And also there will be two first derivative, delta ux by del x will be 0, and delta uy by del z will be equal to 0. So basically, when you will apply all these things into the matrix, then what you will remain with is sigma ij will be equal to this particular matrix, where the only non-zero terms will be this, and this. So basically, as I told you, that the Tx will be equal to sigma xz, that will be equal to 0. So you can see that Tx that is sigma xz, and sigma xz component is this, and that is basically 0. And Ty is sigma yz, and sigma yz is basically this term, that is nothing but that is what you can see, it is equal to mu del uy by del x, because del z, because del uz by del y, that will be equal to 0. So you will be remain with mu del uy by del z here, and that is the non-zero term, and this term is 0. And now that Tz will be equal to sigma zz, and that is also 0 here. Okay, so that we have seen that only the non-zero traction that is in y direction will be mu delta u by del z. Now we can easily apply the boundary conditions for the traction across the interface, that is t minus z is equal to 0 is equal to t plus z at z is equal to 0. So as we have seen that the traction is in the yz direction, yz plane, or at z is equal to 0 will be mu del uy by del z. And when you will take the value of this from the equation, harmonic wave equation that we just saw in the previous slides, then it will become something like this. Similarly, sigma yz plus, that is basically this thing, and when you will equate them together here at z is equal to 0, then it will become something like this. So this will give another equation for b1, b2 and b dash. And the first equation that you had was b1 plus b2 is equal to b dash, that came from the continuity of the displacement. And we can define now the reflection coefficient capital R is equal to b2 by b1, because b2 is the amplitude of the reflected energy and b1 is the incident energy. Transmission coefficient capital T, that will be equal to b dash by b1, and b dash is the transmission energy and b1 is the incident energy. Now when you will incorporate that, then what you will get R is equal to mu1 R beta 1 minus mu2 R beta 2 divided by mu1 R beta 1 plus mu2 R beta 2, and transmission coefficient you will get mu1 R beta 1 by mu1 R beta 1 plus mu2 R beta 2. So now you can see that this R beta 1 or R beta 2 can be written in this form, that is Cx cos ji by beta I. So let's suppose if you are writing for the medium 1, then it will be R beta 1, that will be equal to Cx cos j1 divided by beta 1. Likewise R beta 2, that will be equal to Cx cos j2 by beta 2. And we also know that the beta I is equal to under root mu I by rho I, or you can write mu I is equal to rho I beta I square. So the reflection coefficient may turn up into something like this, and the transmission coefficient may turn up into something like this. And similarly, you can derive the reflection and the transmission coefficient for P and SV waves. And when you follow the similar operations as we have done for the SH wave, then you will get a system of equations or a collection of equations that is known as Zweoprys equation. And this is basically on the name of a German geophysicist, whose name was Carl Bernhard Zweoprys, and he died before these equations got published in 1919. And these equations are prominently used in reflection seismology, and these are the set of the equation that basically describes the partitioning of the seismic wave energy at an interface and due to the mode convergence. So it can be basically used to find out the amplitude of the reflected P wave, reflected SV wave, and the transmitted P wave and transmitted SV wave at an interface. And it also show the variations of the amplitude of the reflected and the transmitted energy with respect to the incident angle, or sometimes it is also known as amplitude versus offset, and it is also considered to be a very helpful technique in the detection of the petroleum reservoirs. So you can see this is the reflection coefficient for the P wave, reflection coefficient for the S wave, transmission coefficient of the P wave, and the transmission coefficient for the S wave. And when you will solve this set of equations, then you will get the reflection coefficient for the mode converted waves. So it is a very important equation that we just see in this matrix form. So now a very important principle that we must need to talk about is the Fermat's principle. And Fermat's principle basically says that the ray path between 2 points are those for which travel times is an extremum, which is a minimum or a maximum travel time. So let's suppose if you are talking about direct wave between source and receiver, it can follow this path, it can also follow this path, and it can follow this direct path. But among all these paths, this is the path which will be having the minimum time. Likewise, when you will talk about the reflected wave, then reflected wave may come from this way, it may also come from this way, and it can also come from this way. So among all these paths, this is the only path which will be having the minimum time, at which incident angle and the reflection angles are equal to each other. So that means this will take this path only. Okay, so this is the Fermat principle, which says the ray path between 2 points are those for which the travel time is an extremum, which is a minimum or the maximum travel time. So the simplest case is the 2 points in the homogeneous half space. The time needed to traverse the straight line connecting the point is less than for the adjacent paths. A second ray path for which the time is minimum compared to the adjacent path is that of the reflected ray, satisfying Snell's law. The direct ray path corresponds to an absolute minimum of the travel time, whereas the reflected ray corresponds to the local minimum time. Now, we can derive the Snell's law from the Fermat's principle. So you can see there is this ray that is incidenting upon this interface separating medium 1 and medium 2, and this is originating from the point 0, A, and the ray where it is intersecting at the interface is basically a point x, 0, and the ray after traveling a certain distance in medium 2 is having this point b, minus c, and this is the incident angle and this is the refraction angle I2, and when we calculate the total path traveled by this ray, then what you can see, you can also calculate the travel time. So total travel time for this ray would be this one. So total path in medium 1 divided by its velocity plus total path in medium 2 divided its velocity. So it will be under root a plus x square by v1 plus under root b minus x square plus c square by v2. When you want to find out the travel time is an extremum, then we will have to differentiate with respect to x and then set it equal to 0. So when we are taking the first derivative with respect to x, then it will become something like this, and this particular quantity is nothing but sine I1 by V1, and this particular quantity is nothing but sine I2 by V2. When we are equating it to 0 to get its extremum, then you will get the Snell's law, that is sine I1 by V1 is equal to sine I2 by V2. Similarly, there is another principle which is famously known as Huygen's principle, because so far we have been talking about geometric ray theory, and in some of the applications geometric ray theory fails. And what are those applications? So let's suppose there is a bending of the waves across the Earth's core, or you can say the diffraction of the wave across the Earth's core. So what you will see that when the diffraction happens, these waves reach in the places of the shadow zones as well. So when they reach to the shadow zone is the zone where the P wave, if you are talking about the P wave shadow zone or the S wave shadow zone, then these waves should not reach over there, but they do. So due to the diffraction phenomena, this is where the Snell's law basically predicts no ray path. Also, similarly, you can say there is no energy should be transmitted when the angle of incident is greater than the critical angle, but there is some amount of transmission happens, and that is where the geometric ray theory fails. But you can find the answers to these questions up to some extent using the Huygen's principle. So Huygen principle, it says that each point on a wavefront can be considered to be Huygen's source that give rise to another circular wavefront. These wavefronts interfere constructively to give a circular wavefront and interfere destructively everywhere else. So in 3D dimension, the wavefront, instead of having its circular shape, it may be considered as a spherical wavefront emanating from each Huygen source. So you can see like this is the position of the wavefront at t is equal to 0, and when we are taking some points on this particular wavefront, then at t is equal to 1 we can make circular wavefronts around these points, and we will join the peaks of this wavefront to make the new position of the traveling wavefront as t1. Similarly, you can find the position of this wavefront at t2 and t3. So basically what it is demonstrating, that the Huygen principle for the propagation of a straight wavefront, successive wavefronts are generated by drawing a circular wave from each point on the previous wavefront and then drawing a line tangent to the circle. Circular wavefronts are assumed to interfere destructively. Now, this is another example that this is the point from which the wavefront is emanating, and it is giving rise to this wavefront where all the points, some points if you consider, then it can behave as a point of the secondary wavefront, and which will generate the circular wavefronts like this. And when we join their travel path, then you can get the new position of the wavefront. So that is how the circular wavefronts can be generated by treating each point on the initial wavefront as a point source of the wave energy. So now, these are my references, and in the next lecture, we are adding one more lecture to this module, and this will be your lecture 6 for module 2, where we will be finishing the Snell's law, transmission and the reflection of P and SV and the SH waves, and then we will move on to the module 3 of the earthquake seismology course. So that is all for today. Thank you so much. Bye bye.